Hey folks, welcome back to the channel, and if I told you that the universe would not exist the way it did without one single law of physics, would you believe me? Well, it's true. That law of physics is the conservation of angular momentum, and without it, our universe would look very, very different. My name is Thomas Rintoul, and I am a master's student in astrophysics at the University of St Andrews in Scotland, and on this channel I talk about physics, astronomy, and what it's like to be a student in the sciences. If you're new, hello! Why don't you hit that subscribe button and the bell icon so you don't miss any of my future videos. Let's get on with why you're here. Meet the universe. At a mere 13.7 billion years old, she's... well, actually, we don't know if she's young or old, actually. We don't have a point of reference. Anyway, the universe is home to many structures that we are very familiar with. Galaxies, solar systems, black holes with those bright bands around them. All these systems are familiar to us. But do you know what they all have in common? They're flat. Oh, not like that, get that away. No, they're flat like this. Our spiral galaxy is made up of a massive disk of gas and dust and stars. Our solar system and others like it have a flat plane where all of the planets orbit around. Even this thing, you remember this from Interstellar? Yeah, it's the black hole, and it's surrounded by a disk, with a side helping of gravitational lensing, which we're not going into today. So why are disks, or these flat planes, so common in our universe? Well, it all comes back to that one fundamental law, the law of conservation of angular momentum. But what is this angular momentum, I hear you ask? Well, before we think about that, first let's have a look at momentum in a straight line. Linear momentum. This is a vector quantity, meaning that it has a direction and a magnitude.
With both direction and magnitude.
Linear momentum is the product of an object's mass and its velocity, its speed in a certain direction. P equals mv, where P is linear momentum. Momentum can be thought of as the object's tendency to keep going in that direction. If something has a very high momentum, it can be really hard to slow it down or stop it or change its direction. Equally, if it's got a very low momentum, it's really easy to stop or change direction. Angular momentum is similar, but instead of it being the tendency for an object to go in a straight line, it's instead the object's tendency to rotate around some central axis. Since there is this rotational element to angular momentum, the equation has one extra term, the distance from that central axis. L equals mvr. This means that if the object moves in closer to that central axis and angular momentum is conserved, which means it doesn't change, the object must speed up, its velocity must increase. Equally, if it moves further away, then it can slow down. It has to slow down because the distance has got larger. This fundamental law, the conservation of angular momentum, is key to why our universe exists the way it does. Along with gravity, of course. The conservation of angular momentum is why so many systems in our universe are found in disks or these flat planes. So, let's talk about how you form a disk. Let's zoom in on our wonderful universe, down from the majestic scales of the cosmic web, right down to a spiral galaxy not unlike our own. Let's look at one of those spiral arms, blue with the starlight of young stars, and peer down on a single cloud of molecular gas. The gas in this cloud has some random motions, some overall angular momentum. Even if it's a small amount, this means it's got some small amount of rotation. Deep within this cloud, these random motions manage to pull together enough mass to form a dense core in the middle of the cloud. This core starts to contract under its own gravity, getting smaller and denser. The small rotation of this cloud has to change. We know that if the distance to the central rotation axis decreases, the gas has to speed up. So it does. Its velocity increases and the centripetal forces pull the gas that doesn't make it into that dense protostar into a nice flat, thin disk orbiting around the protostar, a circumstellar disk. Now, we have a problem. We have a disk around a protostar, not a star. Protostars are small, not the massive behemoths that we see out in our universe. It's not even as big as our sun. So, how do we grow it? You guessed it, the key is angular momentum conservation. We have a lot of mass in the disk. We need to get that onto our star. In our solar system, 99% of the mass is found as part of the sun. Not in the planets, not in all the asteroids, not in all the Kuiper Belt objects. In the sun. We had to get almost all of the mass to get onto our protostar. The only problem we have is this angular momentum. If our gas tries to move onto the star, it's going to speed up. The distance to that central axis is going to decrease, and angular momentum conservation forces our matter, our gas, to speed up. So much that it will never get onto the star. So how do we solve this problem? What we need is a way for our disk, our circumstellar disk, to become an accretion disk, allowing mass to fall onto the star without angular momentum being a problem. Accretion is the process that lets stars and black holes grow. For this to work, we need our mass to fall onto the star, but our angular momentum to flow outward through the disk. But how do we do this? Well, to the rescue is viscous torques, and magnetic torques, but we're going to skip over those for this video. Viscous torques are a result of gravity. The gas in our accretion disk doesn't spin around the star like a DVD. It doesn't rotate as a solid body. Instead, the gas orbits at different speeds depending on how far from the star it's orbiting. Like how Earth orbits the Sun faster than Jupiter does because Jupiter is further away. The further out the gas in our disk is, the slower it's going to orbit. This is the key. Let's think about two blobs of gas orbiting around our protostar. One of them is very slightly closer than the other. One of them, the one closer, is moving ever so slightly faster than the one that's further away. These blobs of gas have mass, meaning they exert a gravitational force on each other. Our faster moving blob is going to exert a force on our slow moving blob, speeding it up, giving it some extra angular momentum. Equally and opposite, the slow moving blob of gas pulls back on the fast moving blob of gas, taking some angular momentum away from it. Fast moving gas now has less angular momentum. Because of this, it has to decrease its distance from the star, meaning that it moves closer in, carrying its mass with it. The slower moving blob of gas has more angular momentum, it's sped up, and to balance this, it's going to move further out, carrying that mass and that angular momentum further out. This process happens throughout the disk. Mass flows are very slightly imbalanced, carrying more mass in than out. Angular momentum is obviously conserved. This allows our mass to flow in overall. This allows angular momentum to flow out, being conserved. This allows our star to accrete. This makes our circumstellar disk an accretion disk. So we need angular momentum conservation. Without this simple law of physics, we wouldn't have galaxies with gorgeous spiral arms. Our early protostars would never grow, never reaching the massive sizes of O and B stars that can die in these spectacular supernovae, producing the heavy elements we need. Without angular momentum conservation, our universe would never form planets, or if it did, they wouldn't last very long before they fell onto their star. Without angular momentum conservation, there would be no civilizations like ours. Our universe? Well, she'd look very different indeed. Thank you for watching the video all the way to the end. Since you made it this far, if you haven't already, then make sure you get subscribed and hit the bell icon so you don't miss any future videos. Over the next few months, you'll be hearing a lot more about accretion because it is the basis of my master's project. Specifically, I'm looking at accretion in systems involving 3 stars. Leave a comment below, let me know if you learned anything new in this video, and as always, I look forward to any questions you might have. If you're looking for something else to watch, then why don't you give this video some love? It's all about how physics makes taking photos right before sunrise amazing. I hope you enjoy it, and I hope you have a very good rest of your day. See ya.